In this video, we're computing the magnetic field at a distance of S from the midpoint of a short wire that has a length of L. So we can see in our picture that that observation point for the problem is along the perpendicular bisector of our short wire. Now, of course, we're begging the question here, how can a current flow in a short wire of length L? And the answer is that it can't. So you can either choose to just not care about that complication, or you can imagine that each end of this wire extends into the page, and somewhere back there, there's a circuit being completed with a battery. So in that more realistic case, what we're really saying is we want to compute the magnetic field component due to this short segment of wire, and then those other pieces of wire that we're not showing are going to produce their own components as well. So notice in our diagram that I've already labeled a little slice of the wire that I called dl vector. So that's a tiny increment of length together with a direction, and for the direction there we use the same direction as the direction of current. This little dl is what's going to give us an infinitesimal contribution to the magnetic field by way of the Biot-Savart law. Another thing to notice in the diagram is that I've already labeled the left end of this short wire as negative L/2 and the right end as positive L/2. And this suggests what I'm doing here is using the middle of the wire as an origin of coordinates, and we're going to call that variable x. This means our little slice of wire, dl, is located at a position of x, and then as we're doing our Biot-Savart integral, we're going to let x go from negative L/2 to positive L/2. So let's take a look at the Biot-Savart law. This is the differential form of the Biot-Savart law where I haven't put an integral sign on it yet. I'm just interested in the infinitesimal contribution to the magnetic field given by that little slice dl. And in the formula, we see a dl crossed into an r hat, and we see an r squared in the denominator. Now what that r is referring to is the position vector that points from our little dl to the observation point. So there's our position vector, r with a vector symbol over the top, and the magnitude of that is r with no vector symbol over the top. And notice that this thing makes an angle of theta with respect to the horizontal. Now the r hat in the Biot-Savart formula is a unit vector pointing in the same direction as this position vector. So that carries the direction of r, but it has a magnitude of 1. Now to figure out the direction of the magnetic field contribution due to this tiny slice of dl, we have to take the direction of dl, which points rightward in this diagram, and then cross that into r hat. So we take the fingers of our right hand and we orient them in the direction of dl, that's pointing straight to the right, and then we sweep toward the direction of r hat through an angle less than 180 degrees, and this forces our thumb to point directly out of the page. So there's our little infinitesimal contribution to the total magnetic field up there. Our dl is giving us an outward contribution. Now you can repeat this process anywhere you want along the wire, and every time you take that cross product, you're going to end up with an outward contribution to the magnetic field. And this means when we add up all the field contributions, we can just add the vector magnitudes together to get the total field magnitude at the observation point. So it's time to start setting up an integral here, and I'm going to get rid of that vector sign over the dB. All I need is the magnitude of this contribution, and then when I add up all the magnitudes, I get the magnitude of the vector sum, again, because they all point in the same direction. So to get this magnitude, I need the magnitude of the cross product dl crossed into r hat. And when you find the magnitude of a cross product, you need to take the product of the magnitudes of the two participant vectors and then multiply by the sine of the angle between them. So that gives me a dl, again with no vector over the top, times the magnitude of r hat, but that's a unit vector. It has length 1, so I don't even have to write that, times the sine of theta, and then divided by the magnitude of the position vector squared, r squared. Now this expression has 3 variable quantities in it. I have a little dl, I have a sine of theta, remember theta is changing, and I have a magnitude of the position vector, which is also changing. So the challenge of setting up the integral is to get everything boiled down to a single variable, and we're going to use x for that. I'm going to go ahead and move the I out in front with our other constants, so I have mu naught I over 4 pi out in front. And then instead of saying dl, I can just say dx. It's a small increment of length exactly in the x direction. And instead of saying the sine of theta, I can go ahead and use some right triangle trig here and say that that's s divided by r. That leaves me with an r cubed in the denominator. So now s joins our constants out in front, and I have a mu naught is out there. And now I can replace my r with the magnitude of the position vector in terms of x. And using the Pythagorean theorem, the magnitude of r is the square root of s squared plus x squared. Well, I'm raising that to the third power. So I have an x squared plus s squared to the 3/2 power down there in the denominator. So now we have dB expressed entirely in terms of a single variable x, and we should be able to add all these up by using an integral. So we just start with a reminder that our total magnetic field magnitude is going to be the sum of all the magnetic field contributions. And this is what an integral does. It just adds up infinitely many infinitesimal contributions and tells you what the total is. So now moving the constants out in front of our integral, I have mu naught is over 4 pi. And then the integral as x goes from a lower limit of negative L over 2 to an upper limit of positive L over 2. And I have dx over the quantity x squared plus s squared to the 3/2 power. Now you may recognize already that this is a classic trig substitution integral, but there's one more simplification I want to do before we start getting into that. Because what I notice here is that we're dealing with an even function in the integrand. If I replace x with negative x, I get back the same function. This means I have symmetry about the y-axis if I made a graph of this thing. And that means I can just integrate half of this thing from 0 to L over 2 and then double the result. So the advantage there is that we really like having zeros in our limits of integration. So the doubling the result part produces a factor of 2, which cancels one of the factors of 2 in the denominator. And I end up with a mu naught is over 2 pi. And then I have the integral from 0 to L over 2 of dx divided by x squared plus s squared to the 3/2. So the trig substitution that we want to make here is a tangent substitution because we're trying to exploit the trig identity. Tangent squared plus 1 gives us secant squared. If we can make that simplification down here in the parentheses, then our denominator is going to simplify and it gives us a good chance of seeing where to go next. So to get that to work, we're going to let x equal s tangent theta. So when I square x, I end up with an s squared tangent squared theta, and then I'm going to factor the s squared out of there, and I've got my trig identity. We also have to transform the differential, so dx is going to be s secant squared theta, d theta. And I want to go ahead and move my entire integral to theta space now. So I need upper and lower limits of integration in terms of theta. So our lower limit was x equals 0. I need to find out what that means for theta. So I go back to my substitution. And if I put a 0 in there, I get tangent theta equals 0. And this occurs when theta equals 0. In my upper limit, this is where things start to get ugly. I have an upper limit of x equals L over 2. If I replace x with an L over 2 up there, I end up with tangent theta equals L over 2s. In other words, theta is the angle whose tangent, the inverse tangent of L over 2s. So we start making these substitutions in our integral. My constants, of course, are spectators here, so those are still hanging out in front. Mu naught is over 2 pi. Now my new limits of integration are going to be 0 to this unfortunately complicated upper limit, inverse tangent L over 2s. And then I replace my dx with s times secant squared theta d theta. And in my denominator, I end up with an s squared tangent squared theta plus another s squared inside this thing that's raised to the 3/2 power. Well, we can factor the s squared out of that while we're going. And raising that to the 3/2 power gives us s cubed. So now a couple s's are going to cancel out. I have 1 out in front. I have 1 in the numerator of the integrand. So 2 of those 3 in the denominator have been canceled out. And then I'm going to move that out in front. So I have mu naught I over 2 pi s out in front. And then again, an integral with an unfortunate upper limit. So I have 0 to inverse tangent L over 2s. And then let's think about our trig identity. So tangent squared plus 1 is actually secant squared. If I raise that to the 3/2 power, then I square root it and cube the result, and I get secant cubed. So then 2 factors of secant are going to cancel, leaving me with a 1 over secant theta in this integral. So things are starting to get really simple now. And then we remember that the secant is the reciprocal of the cosine. So now I just have the integral of cosine theta d theta. integrated from 0 to the inverse tangent of L over 2s. And the antiderivative of the cosine function, of course, is just the sine function. And then we have to evaluate across the limits of integration. So I'm going to mention the lower limit first, because when I sub in a 0 for theta, I get the sine of 0, and that's just 0. So we don't have to worry about that. The only survivor here is what happens when I sub in the upper limit. So when we sub in our upper limit, we end up with a mu naught I over 2 pi s times the sine of the angle whose tangent is L over 2s. Now, whenever you see a trig function of an inverse trig function like this, it should reduce to a nice algebraic expression, and you can get it by drawing a little right triangle. So I'm going to call this angle right here the angle whose tangent is L over 2s. And that means the opposite over adjacent is L over 2s. And the simplest way to get that done is to make the opposite side L and the adjacent side 2s. Now, a little bit of quick algebra with the Pythagorean theorem will give you the hypotenuse. And that's going to be the square root of L squared plus 4s squared. And that guarantees that the sum of the squares of the legs is equal to the square of the hypotenuse. So now we can compute the sine of the angle whose tangent is L over 2s. That's just the opposite over the hypotenuse. So L over the square root of L squared plus 4s squared. And this is our final answer for the result of the Biot-Savart calculation. Now there's one more thing I'd like to do here. In a previous video, we computed the magnetic field due to an infinite line of current, and that turned out to be mu naught I over 2 pi s. So if we take the large L limit of our answer, we should retrieve that old expression for the magnetic field around an infinite line current. So what happens in that large L limit? Down here in the square root, I have a sum of an L squared and a 4s squared. And that 4s squared becomes negligible by comparison to the L squared. This means that square root will simplify to just the square root of L squared, which is L, and the L's cancel. So as usual, we're using a limiting case there to build our confidence in our answer. We've retrieved our infinite line current formula from our finite line current formula by letting L become large. And this increases our confidence that we've got the right answer. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.